All right, so number 11 up there. Focusing there. Okay, so very first thing to do is to draw this picture, right? To tell me, all right, so here's the thing. I'm going to put B there. So standard triangles, the way we're going to see triangles in this class. So we know we can use, what variable can we use for angles? What's the new variable we use for angles? Theta, right? You can also use, another standard thing to use is capital A, capital B, capital C, right? So you can either see theta, you can see some other Greek letters that we haven't seen yet. I think the book even has them. I can't remember, I think the book has alpha. Unfortunately, we know some Greek letters maybe because of like COVID. All the variants are given Greek letter names, right? Like Omicron and Delta. Those are Greek letters. Alpha, beta. So you're going to see some Greek letters possibly. They're just the Greek letter A and the Greek letter B. They're just trying to be all, ooh, look at us, we're using Greek. Okay. So, whenever you see a triangle that you have to draw yourself, that they give you, very often they're going to have angle B is capital, side B is lowercase, and they're across from each other. Just makes it really nice and easy to remember where things go. Pretty much always, angle C is going to be the hypotenuse, and side C is angle C is going to be the right angle, side C is going to be the hypotenuse. So that means this must be angle A, and this is side A. Does that make sense? So that kind of makes sense. If this is angle A, then across from it, I want side A. Just makes it easy to kind of like set this up. So they tell us that sine of B is 1/2. And they also tell us A is 20. So I know sine of B is 1/2 and A is 20. This tells me a lot. That tells me a lot. What is sine fundamentally defined to be? The ratio of what to what? What's sine? Y to hypotenuse. Right? Or opposite. Sorry. I have a bias against SOHCAHTOA. SOHCAHTOA is fine, but it also sucks. So it works, but not a lot. Okay, so sine is the y side over the hypotenuse. So tell me this, so it's the y side over the hypotenuse, right? So can you tell me what side is 1? What side has a length of 1? A, B, or C? B, right? That's the y piece, right? So that's 1. And what side has a length of 2? The hypotenuse. Do you guys see that? Do you guys see that? If I tell you sine B is 1/2, well, sine is a ratio of sides of a triangle. So that's telling me the side lengths. Now, just to be really clear, it could be 2/4 or 3/6, but this is the reduced form, so that's what I'm going to use. It's y over hypotenuse. There, I know those sides. And it's asking me, what's it asking me? Find the lengths of the missing sides. So what's the last one? Oh, we got them all. Wait a minute. Oh, okay. If this is 20, though, this is where things get interesting. Okay. So, all right. Now I see what they're doing here. So this has to reduce to be 1/2, but it could be 2/4. It could be 3/6. Does that make sense? Just has to reduce to be 1/2. The fact that this is 20 is interesting, right? So let's see if this makes some sense. I know that whatever angle, whatever side B is and whatever side C is, it reduces to be 1/2. Is that cool? And again, all right, let's really make sure that you get this. So So here's angle, let's say this is angle A. What is sine A? Seven over 14, right? Which reduces to 1/2. So this could be 7 and 14. You guys see what I'm saying? Okay. Stay with me. This is kind of cool. Okay. So everybody a little bit with me. So again, this is interesting. I really want this to make sense. All the trig functions are ratios of sides of triangles. If you tell me sine of b is 1/2, that actually doesn't tell me what the side lengths are. It just tells me what they reduce to be. So whatever b over c is, it reduces. So it could be 7 over 14. Right? So if they reduce to be 1/2, can you tell me how they relate to each other? Isn't c equal to twice b? Stay with me now. Do you guys see that? If the sine of b is 1/2. Watch this. See how I made those numbers up? 7 and 14? Can you guys, if I put an 8 there, what does this have to be so that it comes out to be 1/2? 16. What if this is 20? What is that? 40. So what if this is b? 2b. Right? If I take that ratio, doesn't that reduce to be 1/2? So the fact they told me sine b is 1/2, sine b is b over c, that has to be 1/2, which tells me c is twice b. Okay. This problem is a little crazy. I love it. All right, so can I figure out what b and c are from that? No, there still could be an infinite number of things. Thanks, Jeff. How else do these sides relate? How else do they relate? Say again? No, I don't know any angles, so that's kind of rough. Oh, to be honest, let me see. There's two ways to do this problem. Let's do this way, and then I'll show you a different way. Okay. There's two ways to do this. I'm in a right triangle, correct? So how do the sides relate to each other? I'm in a right triangle. How do the sides relate to each other? Yes. A squared plus b squared equals c squared. So 20 squared plus b squared equals c squared. Good job, Jeff. Okay. How many equations do I have now that relate c and b? How many equations do I have that relate c and b? Is this one? Does this relate c and d? Does this show me how c and b are related to each other? Yes, right? What's happening? Right? Yes, this. If you tell me what b is, can't I figure out what c is? So this tells me how c and b relate to each other. Is there another equation we have that tells me? Yeah, right there. So tell me real quick. C is what? What is c? You know exactly what c is. What is it? 2b. So what can I put right there? Can I solve that for b? Yes. Okay, so don't worry, I'm going to show you a different way to do this if you don't like this way. So this is sort of a setting up equations, systems of equations, right? Substitution method kind of thing. I'll show you a different way in a minute. Bless you. So let's see what we get here. This is 400 plus b squared equals 4b squared. I can subtract b squared. So we get 400 equals 3b squared. Stop for a minute. Okay, and then you can solve for b, right? How do you solve this for b? divide by 3. So I get b squared equals 400 over 3. So then what's b? What's the square root of 400? 20. And what's the square root of 3? I don't know. So this will be 20 rad 3 over 3. Woo! All right. That's one way to do this. Okay. Let's do this a different way. The reason you can do this a different way is because if I tell you that sine b is 1/2, can anyone tell me what the angle is? What is b? Yeah, I heard it. What is b? I heard it. I think I heard it, right? Somebody said 30, yes? Okay, right? Isn't b 30? The sine of what angle is 1/2? Well, it has to be far away from the y-axis, right? Because where does sine like it? Sine likes y. So to be small like 1/2, it's got to be far away, so it's got to be 30 degrees. So I know b is 30 degrees. Or pi over 6. Whatever you like, right? Those are the same thing. Okay, maybe. And they want me to figure out these things, right? Okay, so, let me see. This way is still going to be a little bit funky. So what relates these two? So I know this is 30 degrees now. What trig function relates this to this to this? Tangent, yes? All right, I want to make sure you guys really understand. The angle's on the base, and I want to figure out what side B is. What trig function relates B to A with this angle? It would be tangent. Tangent's y over x, right? So this would say tangent of 30 degrees equals B over 20. So B is 20 times tangent of 30 degrees. And if you need to, tangent is sine over cosine. If you need to, right? I don't know if you guys remember. Again, you desperately need to have sine and cosine memorized and then kind of build tangent. The way I remember, so assuming you have sine and cosine memorized in some way, right? You have to, if I say what sine is 60, you need to be able to tell me relatively quickly, right? So assuming you have those memorized, what's sine of 30? I think we just did that a minute. Well, we know what sine of 30 is. Sine of 30 is 1/2. What's cosine of 30? Rad 3 over 2. So you see how the over 2's cancel? Is that cool? Do you see how the over 2's cancel? So I get 20 over rad 3, and if I rationalize, I get 20 rad 3 over 3. Isn't that the same thing I got over here, right? Just a different way. What? So. And then you can get the last side just by using Pythagorean theorem. Is that cool? Once I get two sides, I can get the last side Pythagorean theorem. No problem. Yes? Okay. If they would have told me sine B equals 1/3, could I have done it this way? Because we don't know an angle where the sine is 1/3, do we? We know 1/2, we know rad 2 over 2, we know rad 3 over 2, we know 1, we know 0. I don't know 1/3. Then we would have had to have done it this way. Okay, like, not immediately straightforward, but it does force you to use a few things in the same problem. There's multiple things you have to use. So that was a pretty good problem. Let me think, is there a quicker way to do that? No, not really. Okay. Yeah, like 14, you'd have to do it this way. Yeah, okay. Sometimes this book, it's very interesting. Sometimes this book puts the harder problems at the beginning. Normally, the harder problems are at the end. But I've noticed in several sections, the first few problems are kind of the harder ones. Okay. Also, real quick, whenever you have a math book, what do you desperately look for? You look back to see if they have any examples, right? So you would look back to see if they had a problem like that, to see how they did it. Okay. Let me see, does it get better after this? Yes. Like this one is not, look at this. So number 11 and 14, they're kind of difficult. There's multi things you have to do. Look at this problem here. If you solve this problem, if I gave you this problem, you must go, oh, good. Why is that? Why is this one really crazy nice? Like if I want to know cosine of A, well, why is this one easy? Tangent A. Be really careful. Can somebody tell me what tangent A is? Good, 10 over 4, because it's like this, right? So what's the y side? 10. What's the x side? 4. So tangent of A would be 10 over 4. Bam. Cosine of A, what am I missing? Hypotenuse. So you use Pythagorean theorem, right? So if I give you a triangle and I give you two sides, you get the third side Pythagorean, and then you can set up all the ratios. You can figure out all the trig functions. Okay, maybe. Anything else from homework stuff? Yeah, see, that's the same kind of problem. This is the same kind of problem. Let me see. Yeah, let's look at this one real quick. Yeah, let's look at 35. Look at that funky 35. Okay, real quick. 35. Because I'm pretty sure I didn't assign that one, so we can look it up. It wants me to figure out the other angles in this. Okay. My poor little triangles always look like they're melting. All right. 12. Ooh, look at you. A, B, 10 degrees. Okay. Why would tangent not be a good thing to start with here? What sides would tangent relate? A and B, right? Tangent would relate A to B. I don't know either one of these. I would have too many things I don't know. So what's a better trig function of 10 that would relate sides? At least one of them I know what it is. What's a good one to use? Sine. If I do sine of 10 degrees, what is that the ratio of? Yeah, the y side to the hypotenuse. So it would be A over 12. And of course, how do you solve for A? Just multiply by 12. And then you can just, this is not an angle that we're supposed to memorize. So you can do that one in your calculator. So on the next quiz, for example, you will not be allowed to use a calculator. So of course I'm going to give you like 30 degrees, 45 degrees, 60, right? I'm going to give you those angles that we're supposed to know what they are. On the test, if I give you 10 degrees, use a calculator. If I give you 45 degrees, don't use a calculator, right? Give me the actual radical whatever. Are you guys understanding? Does it make sense? So you have to give me the exact answer. In fact, I'll try to say that on the test when I want an exact answer. Okay, maybe. Do you guys see this? This is the power, this is the immediate power of trig. Is if I know the angle and I know one side, I can figure out everything. Because trigonometry relates ratios of sides. I'm good. So does anybody have their calculator with them? I didn't bring them all with me. What is 12 times sine of 10? Make sure you're in degrees, right? I get to show off my new calculator. Ooh. I want to make this into a TARDIS or something. Let's see. Bum-bum. Okay. So what do you guys, anybody able to do that? Yeah, 2.08. If you tried it and you got negative 6.5, you're in radians, right? It should be an immediate problem. You see a negative side length. You should go, oh shit, something's wrong. So this is 2.08. Just around it. How can I get side B? Two ways to get side B now. How could I do it? There's two ways. Give me one way. Say again. Cosine. I can do exactly what we just did. Cosine of 10 would be B over 12. Right? Or, what relates to sides of a right triangle? Pythagorean theorem. Right? Either way. You gotta be a little careful with Pythagorean, because is this actually what side A is? Is that really what side A is? No, I rounded, right? So if you do Pythagorean, it's gonna be a little bit off, but you know, it's good enough for government work. Okay. All right, so those are just, once you learn trig, that's the immediate thing we want to do with you, is to show you, now I'm able to do a lot more with these triangles. Okay. All right, anything else from homework stuff? These are kind of cool looking. This is sort of, yeah, I like this. Yeah, we're going to do a problem like this. Is the Mount Doom problem. We'll do that problem. Yeah, okay. These are like the Mount Doom problem. Oh, that's right. You were trained over here, weren't you? Too bad. All right, so nothing else from homework stuff? Okay, so we're going to switch over to this guy. So has everybody got this from yesterday? Does anybody need this? Okay. We got two problems left. Well, this one we really didn't finish out, but what could I do? So we did this problem, we got side X. What could I do to finish that out? What's the only thing I don't know still?
Why?
Yeah, why? So basically the same thing we're just talking about. What could I do to figure out why? Two different things you could do.
Pythagorean theorem.
Yeah, I could definitely use Pythagorean theorem. I've got two sides. Anytime you get two sides of a right triangle, Pythagorean theorem gets you the third side. Or you could use sine to figure out y. Okay. So you would do y squared plus 36.25 squared equals 40 squared. Right? So I don't know y. I know x is this, roughly. And I know the hypotenuse is 40. Why does it make sense that y will be much shorter than x? Not just because I drew it that way, but why does it make sense that y is shorter than x? Look at the angles. Which one opens more? Do you see how x is across from 65 degrees? Y is across from 25 degrees, right? So the x angle opens more. There's more room for that. The y angle opens a little bit. Less room for that. So I love this idea that it's like a mouth opening, right? The 65-degree mouth is open wider. There's more room for it. Does that make sense? I just want to give you an idea of how do I feel out if an answer makes sense. So This will just be throw it in the old calculator. I'm not even too curious about what that is. Let's see. Where'd you go? Right, so it'll be 1600, that's what 40 squared is, minus 36.25 squared. Square root of that, I get 16.91 roughly. Which is definitely smaller than 36.25. Okay. Maybe. So here, this will be a good review for you guys. Do this problem here. Here, while you guys are doing that, I'm going to give you the updated homework sheet. Some more room here. So you do have two options for your first step. There's two trig functions, well it's really four, but there's two basic ones that relate stuff that I can use. Can anyone tell me which trig function would not help me at all? Cosine would not help me at all, right? Because cosine would be the x side of the hypotenuse. I don't know either one of those. Two unknowns, I can't do that. So which trig function are you guys using? Yeah, if you wanted to figure out what c is, you want to use a trig function that involves y and c, because you know what y is. So if I do sine 35.4, that would equal the y side over the hypotenuse. This is where you guys have to kind of get over something. What is sine at 35.4 degrees? It is a number. So I can divide by it, like I could divide any number. So do you see how I can divide by sine, multiply by c? They just sort of switch places, so I can solve for c pretty easily. Multiply the c up. Divide the sine stuff down. So then throw that in the old calculator. Let's see. Anybody do that yet? 91.49. Say again, sorry. 91.49. 91.49, yeah. And again, we're in this step where we could do either one of two things. I could either use, to figure out what x is, I could either use cosine, or I could use Pythagorean theorem, or tangent. Yeah, I got three things I could do. So then it's up to you. Let's do something different this time. Let's use cosine. So if I do cosine of 35.4, is that right? Yeah. That would be the x side over the hypotenuse. And then I could just multiply the 91.49 up, right? So anytime I'm in a situation where I know two sides of a right triangle, the third side's easy. I just use Pythagorean theorem. But if I also know angles inside of it, that's where trig functions come in. Okay. Pythagorean theorem relates sides to each other. Trig functions relate angles to sides. So whatever the hell that is, let's see. 91.49 stuff times cosine 35.4. I get about 74.58 roughly. What is this angle here? Yeah, how'd you figure that out? You've already got 90 and 35, so then you just have to figure out how much makes 180 total. Yeah. So 180 minus 90 is 90, minus 35.4 is 50, what'd you say, 54.6? Okay, maybe. Okay. All right. So let's look at this one. All right. So it doesn't have to be hobbits. If you hate Lord of the Rings, you can replace that with whatever you like. It just doesn't matter. We are walking towards some mountain, right? We could have hairy feet or not. So at one point, we measure the angle. So I want this to make sense. If I walk towards that wall, right? So right now, if I look straight out, I have to look this far up to see the top of the wall. You guys with me? Obviously, if I walk towards the wall, don't I have to look up much higher? Sort of like if you go to a movie theater, where do you not want to sit? Me right now, I don't want to sit anywhere in the theater, but if you go to a movie theater, where do you not want, well, maybe you guys have a different opinion, but I don't want to sit very front row. No? Does somebody in here like going to the front row? Especially if, so we went, I remember friends of mine and I, we went to this movie theater, and it was something where there were aliens, so they had subtitles when the aliens were speaking. So we were in the front row because we got there late. So it was either read what they're saying or watch what's happening. We couldn't do both things. It was like, oh, shit. Plus, at the end of the movie, you're all like, oh, my neck. Because you got to look like up really high because you're right on top of it. So if they're way back here, they got to look up 32 degrees to see the top of it. If they get closer, they have to look at a higher angle to see the top of it. If I'm right on top of this damn thing, I got to like do this to see the top of it. Right? Maybe. I just want this to make physical sense why the picture is the way it is. Okay. We want to eventually know this. What I know is we were here, and I saw this angle that I'd look up through, and then we walked 1,000 feet closer, and then we had to look at this angle to see the top of it. I have no idea how far away from Mount Doom we are at that point. Are you guys understanding? So I really want this to make, this is kind of cool. I don't know if you remember about a tree. I could start at the tree, and then I could walk so many feet back, and then I can see the angle to see the top, and I could actually calculate how tall the tree is. What if there's something really far away, so I can't get to it easily, or it's surrounded by molten lava or something, right? So I don't want to get right up to it. I can't. So instead what I can do is, okay, now that's the angle I see to get up to the top. Walk a little closer. measure the angle again, and then you can do what we're about to do to figure out how tall the thing is. That's kind of cool. This is what they do with survey work, except they have things that calculate it for them. But, you know, we're going to know the shit that goes into that. Okay. So, this is a funky. Can you guys see how many right triangles there are in that picture? Yeah, 2. Focus. Okay. For the big ass right triangle, right? Do this for myself. Okay. For the big ass right triangle, you guys with me? There's a big right triangle, and there's a smaller. Okay. So for the big dude, what is this side? What's that total length? 1,000 plus x2. I don't know why I call it x2. I just did. So can somebody help me set up a trig function that would relate? Which side do I not give a shit about? Hypotenuse. I don't care about it. I'm not trying to like set up a zip line between me and the top of Mount Doom. Come on down to Hobbit's, right? All I know is how far away I am this direction, and I want to know how tall it is. So that would be which trig function? Tangent relates y to x. So what is the tangent? Oh, that's right. Focus. What is the tangent of 32 degrees? Right? Big ass triangle. You can do it. What's tangent in general? What side to what side? Y to x. Or opposite to adjacent. Blah, blah, blah. So y to x. What's the y side? H. What's the x side? 1,000 plus x2, yes? Okay, so that's one thing we can set up in that one triangle. Now we move closer. Right? We move closer. So now I'm talking about the smaller triangle. So again, I could use tangent, yes, for this guy. Because again, I don't give a shit about this. So what's tangent of 35 degrees? H over x2. I love it. Right? For this guy here, the y side is h and the x side is x2. Okay, now this is, I can feel some of you guys just kind of turning off right now. It's like, okay, this isn't x plus 3 equals 7. It isn't. But it's not that crazy hard either. Can you help me? Which letter do I not care about? I don't care about x, right? Or x2, whatever I decided to call it. Do you guys see that? Which means I want to solve one of the equations for it, because then I can plug what I get into the other one. So that's what's called the substitution method, right? I can substitute x2 because I don't care about it. I want to get rid of it. So which equation is easier to solve for x2? Yeah, how do I solve this one for x2? Can't I just multiply this up and divide this down? So if I multiply this up and divide this down, they just sort of switch places. So now I know, I need more room. Scheisse. Now I know x tangent, no, get out. x2 equals h over tangent 35 degrees. That's what this tells me. Now before I plug it in, let's do a little work with this top one. Aw, poor little dude is dying. Somebody's dying. All right, there we go. I want to look at this first one again, real quick. I want to make it a little bit better. It's a little sucky because it's got a fraction in it, right? So I want this to make sense. I'm going to do the same kind of thing. I'm going to kind of swap these. Does everybody see why I'm allowed to do that? Because if I multiply this up, I can at the same time divide this down. So these just sort of switch places. So I get 1,000 plus x2 equals h over tangent 32. And this equation, let me just write it again here. x2 equals h over tangent 35. So I understand right here, this is a great place where students sort of switch off. Because we're now getting away from the physical picture and we're just sort of messing with equations. Oh well, these equations are still physical things. We're just manipulating the variables, right? So can I rewrite number 1 now? Do I know what x2 is? Yes. What's x2? H over that. So what can I put right there? So it's 1,000 plus x2, which is this. Okay, maybe. Okay, so this should not be surprising. This is pre-calculus. We're going to have a lot of manipulation of stuff, right? You have to kind of get over this. In general, how do I solve an equation for a variable? Don't I get everything that has that variable together on one side? So can somebody tell me which piece is in the wrong place? Yeah, this guy's in the wrong place. He's over here with the number. I need him over there with the h shit, right? So if I subtract him, okay, now, can somebody tell me how many h's are up there? 2. Nope. Sorry, I set you up for that. I'm evil. There's one that has been distributed, so I can undistribute it. This is how you solve any equation that's got more than one of the same variable. Can't I take an h out of that? Now be really careful. When I take an h out, what's left? 1 over minus 1 over. Now, is that pretty? Is it nice? No. But how do I solve for h now? I just have to divide by the stuff I don't want, right? Now, the stuff I don't want looks gross, correct? I don't really care because I'm just going to throw it in the old calculator, correct? The angles I gave you are not angles that we had to memorize. So you're allowed to just throw it in the calculator. You can see that? So I almost don't care that it's gross. Who gives a shit? I'm going to let the calculator work it out, right? So I get h equals 1,000 divided by this, which is exactly, whoops, I'm going to put in the old calculator. So I'm going to put in the old calculator 1,000 divided by 1 divided by tangent 32 minus 1 divided by tangent 35. I put it in there exactly the way I wrote it down on my paper, and I get that. Now, I'm pretty sure, it's been a little while since I made this, but I'm pretty sure I actually looked up in the books how tall the mountain was supposed to be. You guys can check me. I'm pretty sure that's how tall it was supposed to be, in case I have any Lord of the Rings people out there. 5,807.66, what was the units here? Feet? Yes, feet. Chihuahua. If I wanted to know how close we were, could I figure that out?
Yeah.
How?
Tangent.
Yeah, look up here. right? We know the height now, don't we? So then I can just go back up here. If I wanted to know how far away we were, I could divide that height by tangent 35, right? Which is basically what you're going to do, but we already have that sucker sitting there. All right. Was that easy? No. Was that crazy hard? No. You just have to realize trig functions are just one more thing that we're going to manipulate in equations. The way you work with equations never changes. We just have some trig functions in there now. I don't care. You still work with the equations the same way. Maybe. So I really want you to understand this. That is one of the more difficult trig function problems. It is. You with me? That is one of the more kind of complicated problems. So don't think that's like your standard problem. Okay. Maybe. Maybe. Okay. So there's no questions on that. I need to get into the next stuff, which is chapter 8, which is where we start doing stuff with the graphs of these functions. Okay. So let's do something. Let's remember what we did yesterday. So if I wanted to graph the basic sine function, let's say I want to graph it from 0 to what? 2 pi. That makes sense to start with. If it's an unshifted thing, 0 to 2 pi is complete travel around the circle. Now, does that mean it starts at 0 and stops at 2 pi? Can't I have negative angles? Can't I have keep going, keep rotating? So the sine function, of course, goes forever in both directions. But we just have to graph one image of it, because then it just repeats that image forever. What did we call this for the sine function and the cosine function, Noah? This is the what of it. This is how long it takes it to go through one cycle. So that is the what of it. Period. Good. So the period is 2 pi. That's how long it takes for it to go through a complete cycle. So how do I break this up? How many parts do I break this up into? 3. I see what you're saying, but 4 really, right? So this will be if I cut it in half, and if I cut that in half, and what goes here? 3 pi over 2. Okay. Those are the main anchor points, or what it does at those values. So remind me a couple things. Sine can only go up to what and down to what? 1 and negative 1, which makes sense because it comes from a unit circle where the radius is 1, so it can't go outside the circle. So it can only go between 1 and negative 1. What does it start at? What's sine of 0? 0. Sine of pi over 2? 1. That's where it's all positive y. Sine of pi? 0, because now it's back on the x-axis. Sine doesn't like x. Sine of 3 pi over 2? Negative 1, because now it's down below. So it's negative 1. And then sine of 2 pi? 0 again. So it goes like this. Whee! Cosine is the same thing, except it's just shifted back pi over 2. So it sort of starts at 1 and then goes down and up. Right? I kind of think of a cosine function. Well, it doesn't really look like this, but it sort of looks like this. Doesn't that look like a really simple octopus? I don't know. Really, like looking on, it hasn't lost a lot of eggs. You're just looking legs. You're just looking straight at it. No, if not, it's okay. That's just me. All right, stop. Okay. we're going to do some stuff to this thing, just like we've done before. And I just want you to remind me real quick. If I had this function, right, and it looks basically like this. This is nowhere near good enough, correct? If I ask you to graph this, this is bad. You're going to lose almost all the points. But it's good enough for right now. That's what it looks like, yes? That's what a square root function looks like. What would this do to that graph? What would this do to that graph? Oh, shit. Oh, shit. Oh, shit. Let me start off this. Okay, this might be too evil to start off. What would this do? Say again? I think he said, which direction? Which direction? Right, yes. Right one, yes? Okay, because when it's inside with the x, it kind of does the opposite of what it looks like. All my inputs have to be one bigger than they used to be. So that would be right one. So that would look like, what would this do? You don't have a lot of colors, Chef. That's all right. It's all right. See if you can make stuff. Yeah, okay. So again, let me ask this again. What would that do? Not quite. If I'm doubling my inputs, if that's the first thing I do, can't all my inputs be half as big? Does that make sense? If I have this function, how do I make an output of 4? What does x have to, I'm sorry, let's say, what kind of given? What's the input got to be so the output's 2? 4. What's the input got to be here so the output is 2? 2. Because the first thing I do is double it. So don't all my inputs, can't they all be half as big as they used to be? That's why that smooshes it. So this would smoosh it, so it would actually look like, so this would actually look like this. It just pushes it back. Okay, maybe. It smooshes it, right? Okay, maybe. So it doesn't matter what the function is we're looking at. The transformations always do the same stuff. So, if I had this function, what would that do? Yeah, I like it. Okay, I see what you mean. Anybody else? What would it do? What did this do? I put a 2 in with the x. It smooshed it. So what is this going to do? Yeah, it's going to smoosh it. You can use the word smoosh. Or if you compress, right? Maybe. This is really cool. I want you to get this. So normally it takes it 2 pi to complete a full cycle. Yes? Now it's going to smoosh it by what factor? A factor of 2. So where will it complete its cycle now? Pi. So now I can cut this up into 4 pieces. So now it's going to be 0, 1, 0, -1, 0. This poor little marker. That's a little extreme, Jeff. Man, poor little dude. Yeah, so what you did, Nicholas, I like it. This would make it go crazy, right? This would increase the frequency of it. So what was the period to begin with? 2 pi. What is the period now? Pi. Why is it pi now? Because it's going to be half of what it used to be, yes? So what if I put a 4 there? What will the period be now? It was 2 pi. Now I'm going to cut it by how much? A factor of 1/4, right? 4. So now it's going to be pi over 2. So now it's going to do its whole cycle in here. So now it's going to be 1, 0, -1, 0. So now it's going to go. Now it's like really, yes, maybe. So if you were doing sound, if you were working with sound, this is what you would see on your oscilloscope, on your equipment, if it was a really high-pitched frequency. This is a high frequency, right? Okay, maybe. Okay, one more of these. What if it was, let me see, I think I have a good green one. Yes, okay, I think there's a good one. Yes, okay. What if, so now I gotta come up with a new letter. Let's see, let's say m of x is sine of 1/2 x. What's that gonna do? Yeah, it's gonna stretch it out. So we basically have developed a formula to figure out the new period. It'll be the original period divided by whatever this number is. So now it's going to go to 4 pi. So now it's going to be, if I cut this in fourths, this will be the midpoint, and this will be the intermediate points. So I might have to do this over. Let me see. Yeah, let me draw it differently. Okay. May not put it all in the same graph. It's getting a little crazy. Okay, so now it's going to go up to 4 pi. The beautiful thing, though, I really want this to make all the sense in the world. It will always hit those 4 major plates. You can always break it up into 4 parts. Whatever the period is, you can break it up. So halfway is 2 pi. This is pi. This is 3 pi. 1, -1. So now it'll be 0 here, 1 there, 0 there, -1 there, 0 again. So now it's been really stretched out. Just pulled it apart instead of smooshing it. Okay, maybe. Okay. So that would be, where'd it go? That. Let's see. Okay, green, you're pretty good. I'm going to stick with the floor. Erase all this crazy stuff. Try to. Oh, you're all terrible. Okay. Okay, so now I know if I have this, I use the letter K there, I know that my period will be 2 pi divided by K. So it's what it was originally divided by that number. In fact, let me see, I can do this real quick maybe. I forgot I was going to do this earlier. Damn it. Yeah, okay. So see, so sine kx, yes? Sine kx. It's kind of tiny. Can you guys see? So I just put sine kx in there, and then I can add a slider. Desmos kicks so much ass. So if I make k bigger, it smooshes it. Look at that. It's kind of nice. Let me see. So sine kx. If I make k bigger, smooshes it. So as I do this, I can sort of hear it going. The sound is getting really high pitched. And if I make k negative, I'm sorry, not negative. If I make k less than 1, it stretches it out. Yes? Maybe? Now if I make k negative, it just reflects, just makes a reflection like we know it should, right? The negative inside would reflect it around the y-axis. So see how the sign now goes down now instead of up? Because it's negative? Okay, maybe. What should happen if I add a constant to it on the outside? Oops, let me make this 0. So there it is. Okay, I kind of gave it away. What happens to a function when I have a plus a number outside? What does that change? It moves up and down, right? So if I change C, it's going to move up. It doesn't change the frequency at all. Down. That's amazing. Yes? That's amazing. Shit. Let me put that back to 0. What if I put a number here? And if I change that number in front, the number that's in front of sine. So if I like 2 times sine, 3 times sine, what would that do to the picture? No, it's not negative. So if I have sine, what would twice sine be? Taller, right? So sure enough, if I make A get bigger, it just makes it taller. See that? So now I can hear the sound getting louder. Yeah, sorry, the T was ready. Okay.
Is that frequency in hertz?
Say again?
Is that frequency in hertz?
Yeah, this is like if this axis is time, then it's like per second, cycles per second is what hertz is, yeah. So that's why when I compress it, I get more cycles quicker, which makes the frequency go up. Yeah. Yes, good. So if you know any music or sound or whatever, that's exactly what's happening, right? The quicker the wavelengths get to our ear, the higher the pitch is to us. That's why, you know the Doppler effect, right? Can you make the sound of a car going past me? What's it sound like? Or like an ambulance. You know, like that. Right? Doesn't it get lower? Doesn't it get like a lower pitch when it goes past you? Because now the wavelengths have to come at you. They're traveling away from you, so they're longer when they come to you. When it's coming at you, they compress. So when it's coming at you, it's like, right? Everybody knows that sound of a car going past. Okay, sorry. I'm not going to make this physics class, don't worry. All right, one last thing we can do. What if I put in here something like that? Oops, why did I put A? Shoot. What do I want to use there? I can't remember. I think it's B maybe? Make A1 again. Okay. I'll make B 0. Kind of giving it away, but too bad. So if I put something in there with the X, how's that going to move? Up, down, reflect? Left, right, of course, right? So sure enough, when I change this B, it's going to move left and right. It's the exact same function, it just moves left and right. Okay, I'll stop. Okay. So, there's a lot of shit happening, right? We give these things different names. So we have the word period that kind of refers to how long it takes for it to go through a cycle, right? In fact, let me go ahead, and of course, holy shit, I forgot to turn you around. That sucks so bad. Let me do this real quick. Sorry, everybody sick at home. Or, you know, telling me you're sick, but not really. Okay. So if I change the B, left and right, if I change the A, that's amplitude is what we call this. That's the amplitude. If I change the C, that's just straight up and down. And if I change the K, that changes the period. Now, this one is interesting. The B, we call that the phase shift. If I move it left to right, if it's a trig function, we just call that the phase shift. That's what we decided to call horizontal shift, is phase shift. Just the name we decided to give it. So let me do this. Let me do this. I'm going to give you, believe it or not, I have a handout that kind of captures everything we just said. Sure. It's got two sides, but the first side kind of goes over the various parts we just discussed. Shit. Let me see. So the number in front is A. To get the period, it's 2 pi divided by that multiplier inside, right? I put this here, we talked about this before. If it's a tangent, the period is normally pi, so then you would do the same thing, pi divided by k. Phase shift, that's just the left and right stuff, so that would be whatever this number is. So when you factor the k out, it's whatever that number inside is. So here I got it completely worked out. Now, real quick, there's something really cool that you don't really need, but it's really helpful when you're first starting to do these. Sine and cosine, where do we normally start when I'm graphing? Where do I normally start and where do I normally end? I normally start at 0, and I normally end at 2 pi, right? So something really kind of nifty that you can do. If I make, do you see what's inside that sine function up there? What's inside of it? Isn't it kx minus b? Isn't that inside the sine function, right? So when the inside of the sine function is 0, that's where I start. And when the inside of the sine function is 2 pi, that's where I end. So what's really kind of cool is you can figure out, just by doing this. So for example, this one. There's the inside, yes? So let me do this right here, and then we'll just compare it to what I have further down. When is the inside equal to 0? Can you just solve this for me? Can somebody help me solve this? Yeah, so you could add the pi over, you could divide by pi, right? So then x equals, divide by pi. So what's x equal? 1 over 2, yes. If I make the inside equal to 2 pi, which is where I normally end, and I solve, add the pi, divide by 2 pi, I get 3/2. So normally we start at 0 and we end at 2 pi. This function is going to start at 1/2 and end at 3/2. So can you tell me, just based on what we just did, if it starts at 1/2 and it ends at 3/2, what's the period? 1/2 to 3/2. What's the period? 1/2 to 3/2. How long is that? What's 3/2 minus 1/2? So I can see how long that is. 3/2 minus 1/2. 1. So it's got a period of 1. Let's check that. What's k in here? What's k? Well, it's related to the period, but what's the value of k here? 2 pi. What's multiplying by x? Right, that's what k does. What's multiplied by x? 2 pi. So what's the period? 2 pi over that. 2 pi over 2 pi is 1. We get a period of 1. I really want you to get this. We just got the period a different way. I begin at 1/2, I end at 3/2, so it takes 1 to get through a full cycle. And then we did the period the other way, 2 pi divided by k, and we still got 1. So it's kind of nice to be able to kind of verify in 2 different ways. You get the same thing. Okay. So that's the period. The amplitude, of course, is 5. So now instead of going from -1 to 1, this function is going to go from -5 to 5. You guys with me? Maybe? The phase shift, so here's the trick. To figure out how much it shifts, I need to figure out how much x is affected. So I need to factor the inside. I need to do this. I need to factor the inside. So I just need to take a 2 pi out. So now I can see my phase shift is right 1/2. So somebody remind me, where does sine normally start? Where do we normally start sine off? 0. What did we figure out here? Doesn't this start at 1/2? We knew that before, but look at what this says. What does this say should happen? It should move which way? How much? To the right 1/2. So that matches too. That matches right there. I know it's supposed to move to the right 1/2. I normally start at 0, so now it should start at 1/2. That's exactly what we got up here. Okay, maybe. Okay. So here's the little check. 3/2 minus 1/2 is 1, which is the period. That's awesome. So now I know I start at 1/2 and I go up to 3/2. That's 1/2 and that's 3/2. So then I just cut that into 4 parts. So in between 1/2 and 3/2 is 1. What's in between 1 and 0.5? What's in between 1 and 1/2? What's in between 1/2 and 1? What's right in the middle?
Is it 1 and 1/2?
Yes, what's in between 1/2 and 1? What's right in the middle?
1.25? No, 0.75?
0.75, yeah, 3/4, right? 3/4. So this should be 0.75 here, right? So I go by, watch, okay. I know I'm throwing a lot at you. When I have a normal sine function, let me see, do I have one up there? No. When I have a normal sine function, doesn't it go 0 to 2 pi? So when I have a normal sine function, do you see how every step is like 1/2 pi big? Every step I take is like 1/2 pi to step through. Okay. So now, since my period is 1, every step is going to be 1/4 big. So every step I take, sure enough, is 0.25, 0.25, 0.25. So it's got the exact same shape. It's just been moved over and smushed. It's got the exact same shape, though. Maybe? All right, let's try one. Let's look at the other side. Let's try a fresh one here. I put some more information up here. Basically the graph that I made on the other page, right? Up here. So let's just look at this thing. So the very first thing I ask you to do is factor the inside. What can you take out in the inside? This would be a little bit weird maybe, but what can you take out? What can you factor out? A 1/2, right? That would leave you with x, which is what you want. So if I take a 1/2 out, I'm left with x minus what? Take a 1/2 out of it. Yes. So what is K? What's in the right place to be K?
1/2.
1/2. That's the multiplier. That's going to affect how much I stretch or compress. So K is 1/2. Can somebody just tell me what the amplitude is? Just that's the easiest part of this. 2. So just to make sure you understand what that really means. Well, you guys tell me. It's going to go how far down? -2 up to 2. So the amplitude isn't this whole thing. The amplitude is how far away from the middle it gets. So it goes 2 up from the middle and 2 down from the middle. So the amplitude is just that much, right? Okay. Sort of like a radius, maybe, from the middle out. That's what the amplitude is. Okay, okay. Okay. So what's the new period? It's always the old period divided by K. What is 2 pi divided by 1/2? 4 pi. I like it. So that's the new period. So now this is stretching it out, right? Normally it gets done in 2 pi. Now it's going to have to go through, get done in 4 pi. It's now double what it normally takes. Okay. And what is the phase shift? That's just a fancy name for left and right. How much do I shift this to the left or right? You guys see what's being done to the x on the very inside? Pi over 4, which way? Right, exactly. I love it. So this will shift by pi over 4 to the right. Now again, the more you do these, the less you're going to need to do what I'm about to do. But this is a really cool little thing to do. It kind of verifies everything you've done. I really want this to make sense. So cosine. We normally start at cosine of 0, and we go up to cosine of 2 pi, correct? So we always start where the inside is 0, and then we end when the inside is 2 pi. I really want that to make sense. Correct? Isn't that exactly how we've been doing these so far? So, what is inside? Isn't this inside of cosine? And so I want to start when this is 0, and I want to end when that is 2 pi. Now, to be really honest, this step here is unnecessary. But again, it's really nice to be able to do this, just to make sure everything you've done so far is correct. Can you solve? Take a minute, please, and solve these two equations. Solve it for x. It's not the prettiest equations ever, but oh well. All right, let's see. So if you solve this, I can add pi over 8 over. Then I just have to double both sides. And that becomes pi over 4, right? Why does that make sense so far? Because I normally start at 0. What was the phase shift?
Pi over 4, right?
So now I'm going to start at pi over 4. Do you guys see that? So again, do you see how it's unnecessary But it is nice to verify what the shit you just did. It's nice to see the same number come out two different ways. Now let me see. Well, let's do this. If I do this, this is a little bit grosser, but let's do one thing real quick at the beginning. I'm going to multiply both sides by 8, just to kill all my fractions, right? So I get 4x minus pi equals 16 pi. I get 4x equals 17 pi. I get x equals 17 pi over 4. I don't know if you guys see that. So anytime you have fractions in an equation, you can kill them. Just straight up murder them, right? Can somebody tell me, based on this, just this, what's the period? How far apart are these? What's this minus this?
4 pi.
Yeah, this minus this is 16 pi over 4, which is 4 pi. That would be the period. What did we get for the period earlier? We got freaking 4 pi. I mean, so again, some of you guys might see how this is completely unnecessary. But again, doing this is really nice. It helps you see that you're getting the same stuff you got before. All right, let me show you one extra little thing. So here's what cosine normally looks like. So now we're going to shift it, and we're going to stretch it. So there's a lot going on to this poor little dude, right? So let me see. Let me help you out just a little bit. My period now, let me put new period, is 4 pi, correct? Which means my step size, oh shit. How big is my step size for the normal thing? Isn't it pi over 2? There's pi over 2, another pi over 2, another pi over 2, another pi over 2. Do you guys understand what I mean by how big each step is? So to figure out how big each step is, I just take the period divided by 4. Because isn't that what we do? Then we cut this up into 4 parts? 1, 2, 3, 4 parts. So if and again, this isn't really necessary, but it's nice. The step size will be 4 pi over 4. It'll be pi. All right. What the shit does all that mean, Jeff? Okay, so the scale's a little bit evil, but I'm just going to sort of ignore it a little bit. So I want to start at pi over 4, correct? You with me? Maybe. Yeah, the scale is kind of evil. Don't worry about the tick marks. I should have left it tick markless. So instead of taking a step of pi over 2, I'm going to take a step of pi. So if I take a step of pi, what's this? So what I mean is, I'm going to add pi to where I am currently. Because normally, what do? 0. Add pi over 2, add pi over 2, pi, so forth. Just get the points. Now I'm going to add pi every step because everything's been stretched out. I'm taking bigger steps now. So what's pi over 4 plus pi? You could do it. 5 pi over 4. Okay. 5 pi over 4. Take another step of pi. Do you see I'm just adding 4 pi over 4, right? So take a step of 4 pi over 4. Isn't that 9 pi over 4? Take another step of 4 pi over 4. Isn't that 13 pi over 4? And then take one more step of pi over 4. Isn't that 17 pi over 4? Why am I happy to see that number right there? Why am I happy to see this? Because that's where I'm supposed to end, isn't it? See that? So again, you've got all these checks and balances. If you do all the stuff that I'm telling you to do, you've got some stuff. When you do it, you can see, okay, I ended up in the right place, good. Everything's kind of helping you check yourself. Check yourself. Now, what's the amplitude again? 2. So you go from -2 to 2. And what does cosine start at? It starts at 1, right? So where I start, I'm going to start. So now I'm going to start at 2. And then where does it go? 0, and then it goes to negative, in this case, negative 2, and then it goes to 0, and then it goes to 2 now. That's why we break it up into 4 parts, because that's where it is 1, 0, negative 1, 0, 1. And then I just have to fill it in. And of course, I mean, this just means it keeps going for forever in both directions, right? Maybe. Let's see. Let me think. Yeah, before 12. Okay, that's about here. Yeah. Okay, let me see. Okay, this is pretty good. So let me show you this. I did it in Desmos just to kind of check. That's what I get in Desmos. So see, this point here is pi over 4, 2. And then this point is 5 pi over 4, 0. 5 pi over 4, 9 pi over 4. 13 pi over 4, and then finally, 17 pi over 4. So I can kind of check my work.
You know how it's cosine? If it was like tangent or sine, would it look any different?
Yeah, sine. So watch this. I can just change it here. So watch what happens if I just change this to sine. See how I moved over? The sine and cosine are off by 90 degrees. So it's the same picture, just moved over, because sine starts at 0, but cosine starts at 1. So they're sort of offset. Right? Now, if it was tangent, does anyone remember what tangent looks like? Just tangent of theta? What the graph looks like? Looks cubish, right? So it would look completely different. But the same kind of stuff would happen. I would move it around, shift it up and down, right? I can smoosh it, and I can pull it apart.
You know, what about like secant?
Okay, good. Now that's the good question. Okay, so now watch this. Let me come back. I kind of have a little word about it at the bottom, about cosecant and secant. If this question had said secant here instead, if that question had said secant instead, I would have done everything we did. I would have done all the same work. I would have graphed the cosine function, but to be honest, let me see. I wouldn't have done it like this. I would have done it, let me see, I would have done it like this. Dotted. Because then, how does secant, does somebody remember how secant works? Wherever cosine is 0, there would be a vertical asymptote, right? And then it would look like this. So that's the great thing about secant and cosecant. If you just graph cosine or sine, just graph it, and then put the little u's on the top and the bottom, you're done. There's nothing special about cosecant and secant. There's just one extra step at the end. So that's what I'm trying to say down here. First, graph the corresponding sine or cosine, and then I love the way I say this, plop our u's down on top and bottom. Right, so you would just plop, plop, plop. So that this would be secant mess. Okay, I like it. So it's just one more step at the end. Crazy sauce. Okay. So let's do one more example, then I'll let you guys out of here. We'll do it up on the board. We'll do it live. We'll do tomorrow we'll focus on tangent, cotangent, right? But cosecant and secant are basically just one more step after cosine and sine. That's beautiful. But right now, let's just do this. Can you guys, if I gave you this, next. Look at all that yumminess. That was creepy too. Let me ask you, can you, amplitude, you gotta be a little careful. Period, phase shift, I'm just gonna call PS, right? Shift up or down. Okay, can you figure out all those things? Basically, the first thing you want to do is you want to factor the inside. Just to make sure everybody does this correctly, what can come out? What can come out? Pi. Okay. So do those. Tell me what those are. Really careful. What is the amplitude? It's 2. What's the negative do? Flip it. Okay, so amplitude can't be negative. It's just the distance I get away from the middle line. The negative just means flip, so the amplitude is 2. So now it's going to go from -2 to 2. Amplitude is 2. What's the value of K? Pi, so what's the new period? Old period divided by K, 2. So now it's going to complete a cycle in a length of 2. What's the phase shift?
1/4
to the left. And does it shift up or down? What's the vertical shift? Up 1. You can see at the end there. So that's the last thing I would do is this. That's the last thing I would do. Everything blah, 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 and then just go, right? Just move it up 1. Can you do the begin and end cycle? What's the inside? Isn't it this business? So when the inside is 0, that's where we'll start. And when the inside is 2 pi, that's when we'll end. Now this is an extra little thing I kind of put on top of this. You're not going to see, I don't think the book shows you this, but I just like this because it really helps you, you know, check everything you've done so far. Do you see how the pi's cancel? Why does that make sense so far? Because what was the phase shift? Left 1/4. So I'm starting at -1/4 now. Okay, so far it makes sense, right? Shift maybe go back 1/4, and that's where I'm starting. It's -1/4. Okay, cool. First thing I'll do here is just kill the pi's, right? Is that cool? I'm gonna kill the pi. So I get x plus 1/4 equals 2. So x equals 2 minus 1/4. Seven fourths. So I'm going to start at negative 1/4, going to end at 7/4. Real quick, how far apart are these two?
2 pi.
No. What's 7/4 minus negative 1/4? 7/4 minus negative 1/4. 7/4 plus 1/4. 2. Yeah, it's 8/4, which is 2. Right? Just 2. And why does that make sense? Because that would be the period, and what did we figure out for the period? Hey, cool. See, I can see shit happening. I can see stuff agreeing with itself, which is nice. Okay. Maybe. Let's see. Yeah. Okay. That's enough for now, I think. So next time, I'll have some more examples of this. We'll kind of work out together. We'll talk about tangent, cotangent stuff. By the way, so everybody got an updated homework sheet, right? So notice there's a lot of extra credit sprinkled around just to try to help us get through enough of the material, right? What else did I want to say here? Shoot, I forgot. Oh, next test is up here. Let's have a, I do want to have a quiz. I want to have a quiz. Yeah, quiz on Monday. Not Monday, that would be evil. Tuesday. Oh, let's see, what was the last quiz? It was 6, 6, and 7, 1, right? So we're going to do the rest of 7. So it'll be 7.2. Well, I'll make it 7.2 and 7.3. Shit, I can't remember. It might have 7.4 on it too. We'll see. We'll see how I'm feeling. 7 point. Become a 0.4. There we go. So quiz on Tuesday. I'll also have the practice test on Tuesday because Wednesday is the review and then Thursday is the next test. Cool. Okay, that's plenty. See you guys next week. Have a good weekend. Have a good Halloween. Whatever you're doing.
How do you do secant on the calculator again?
Secant?
Like secant?
Oh, yeah. So if I had to do, for example, if I had to do secant of pi over 4, it would be 1 divided by cosine of pi over 4. Yeah, blah, blah, right? Yeah. So if you have to do cotangent, it would be 1 divided by tangent of whatever. Yeah. You're welcome. All by myself.